So far, we've taken a look at how we can construct models using differential equations and some of the applications of differential equations, but we haven't talked about how to solve differential equations. In this video, I want to get some insight into exactly what those solutions are going to look like. And we're going to start not by actually solving problems directly, but by trying to sort of solve them graphically, get sketches of what the solutions look like. And the tool we're going to use for that is called a direction field. So that's what we're going to focus on here. For the time being, we're just going to consider first order differential equations. That's all that you can really do as far as direction fields are concerned. And then we'll worry about second order and higher order differential equations later down the line. But for now, first order differential equations, and we will be trying to find pictures of the solutions using direction fields. So we want to essentially get graphical solutions. To ODEs. And so for now, we'll stick to first order. Okay, so basically the idea is the equations that we're going to look at take the form of the following. These take the following form. We're going to have our derivative, in this case dy dx, equal to some function that can be a function of both x and y. What it means to solve this differential equation is to solve for y. So solving means finding the y, the function y. And in this case, hopefully it's clear, dy dx, we're taking a derivative of y with respect to x. X is going to be the independent variable. So we're trying to find y of x in this particular case. Okay, so essentially, if we can figure out what y of x is, our function, we can graph it and have a picture of what our solution looks like. The way we have it all set up, though, is what we're given is a slope. So we're given what dy dx is, the slope of our solution, in a sense, and it's equal to this function f. So a way we can think about this f of x and y is that this thing determines the slope of the y of x that we're trying to find at any given xy coordinate. So this gives the slope of y of x at any point x comma y. So I think the easiest way to talk about this is via demonstration, looking at an actual example. So let's look at an example and see how this might play out. I'm going to start with a simple one. I'm going to say, for the sake of simplicity, let's start this one as just dy dx equals y. So notice my f of x and y is very simple in this case. It's simply just y all by itself. And to get a direction field, to get a sense of what this solution is going to look like, all I'm going to do is basically prescribe the slope at a bunch of different xy coordinates and then graph that. So let me start with a set of axes. So here's my x and y axes. And let me put some points that we're going to be interested in. So we'll be interested in the origin, maybe the point 1, 0, 0, 1, 1, 1. So ideally, if you had graph paper, that would be the way to go if we were trying to do something like this. So I'm just going to put in some points here. And these are going to be the points of interest where I want to kind of find what the solution looks like at a whole bunch of points. And so far I filled up the first quadrant, but we'd probably want some down here in the fourth quadrant And essentially all I'm doing here is creating sort of a dot matrix version of graphing paper. Maybe we want some negative x values back here in all the other quadrants. So far I haven't done anything but plot a bunch of points. These are going to be the points where we try to get a sense of what the solution looks like individually at each of those points. And so what I'm going to do is start with a table over here. I'm going to have the x-coordinate, the y-coordinate, and then basically dy dx, which is the slope. And I'm going to make a table out of this. Oops. So here is my table of values that I want to plug in. So let's start at the origin, at the point 0, 0. What is the slope? So I come over here to the equation, and I notice that my dy dx is simply equal to y. So the slope is just whatever the y value happens to be. And that tells me that basically in my slope column here, what is dy dx equal to? Well, it's always equal to y. So it's the value in this column is going to just match the value in this column because it's always going to be the same as y. So let's just do a bunch of points, maybe the point 1, 0, 0, 1, 1, 1, maybe the point 0, 2, 0, 3, 0, -1, get some interesting values. And let's go figure out the slopes. So we just said the slope is just equal to the y value. So I'm just going to copy down the y column. So this slope is 0 because dy dx is equal to y. So this 0 is equal to this 0. Same thing here. It's going to be 0 again, matching the value of y. Here it's going to be 1, matching the value of y. Here it's going to be 1 again, matching the value of y, and so on and so forth. So I'm just matching the value of y. This column winds up matching this column. Again, that's just unique to this problem based on the way that dy dx was defined in this problem. If this was a more complicated function, we would plug in the corresponding x and y values and basically just plug in whatever into our f of x, y and plug down the evaluated function value f of x, y into this column here. Okay, so now that I know the slope at these points, I want to go draw basically a little line segment with that slope at each of these corresponding points. So the first point I'm going to go to is the point 0, 0, which is the origin point. It's sitting right here. And let me change color so it's a little easier to see. I'm going to do this in red. I apologize if there's anybody with colorblindness issues and you can't really see this. Hopefully the lines will be clear regardless of color. But email me or something and let me know if trying to do things by color is making it hard to understand what I'm doing. So at the origin, the point 0, 0, the slope is 0. And what does a line with a slope of 0 look like? Well, it's just a horizontal line. Let me make that a little thicker. So it is a horizontal little line segment that I've drawn there. Now I'm going to go to the point 1, 0. So that's this point sitting right here. It also has a slope of 0. So let me draw that one in. Let's go to the next point. So I've done this one, I've done this one. Let's go to this point, the point 0, 1. So the point 0, 1 is this point right here, and the slope is 1. So let me draw a little line segment with a slope of 1. A slope of 1 is about a 45-degree angle, so that's what that slope right there looks like. It'll look the same if I go out to the point 1, 1, because that slope is also 1. So here's the point 1, 1. It has a slope of 1. Then I'll go to the point 0, 2. So that's going to be up here. 0, 2. It has a slope of 2. That's even steeper than the 1. So let me draw something that's a little steeper. By the time I get to 0, 3, I'll have a slope of 3. That's even steeper still. And if I go down to the point 0, -1 down here, it has a slope of -1. And then similarly, this one would have a slope of -2 and -3. And what we'll notice as we start to draw these lines in this case, there was no dependence on x. Our slope does not depend on x. Our slope is just the y value. dy dx equals y. So this column is basically irrelevant. All I care about is what the y value is. So for any different x coordinate that I want, the slopes are going to look like copies of this sort of column of slopes that I've drawn here, because all we care about is the y value. Notice this one matches this one. This one matches this one. This one right here will match this one, and so on. So we can kind of go through this and fill in the rest of these point by point by point. And again, I'm filling these in. I know all of these because, again, the slope I'm picking only depends on the y coordinate, the y value. So all of these ones with the y coordinate of +1 are going to have a slope of +1. All these ones with the y coordinate of 2 are going to have a slope of 2, and so on. So I'll draw something a little steeper for all of these, a little steeper still for these. Same thing down here. And that's, again, even true all the way into these negative values of x over here. And I'm just totally sketching these, you'll notice. I'm not trying to be very precise. Right, we're doing this by hand. If we were using a computer, which I will show you how to do down the line, we would have a better sense. But so far, I've drawn all of these different slopes and all of these different coordinates. And it gives me a sense of kind of what the behavior of this function is going to be. So now that I've got this entire field drawn, I want to remember that I'm trying to find y of x. Presumably this thing is a continuous function. I have not drawn a continuous function here. I've just drawn a field that this function is going to live in. So to make the actual function, or get a sketch of the actual function, which I'm going to do in another color, let's do this one in blue. Make sure that's thick enough. Let's say I'm picking one that happens to go through this point right here-ish. That might be a good one. So maybe the point 0, 1/2. So let's find the solution that passes through a given point. In this case, I'm going to say the point 0, 1/2. And I, again, just made that up off the top of my head. So that's this point right about here-ish that I'm drawing in blue. If I tried to draw a solution that passes through this point and follows sort of the trend lines that I've drawn here, I would say, well, it looks like it needs to have a slope of about 1/2 as it passes through this point. So it's not going to be that steep, but it's going to be going up. Then it looks like maybe that would increase and kind of go through here. It looks like from this one, it would kind of follow up to this one, and then that starts to get steeper and steeper and steeper. So maybe it'd go something like that. And then as I come back this way, it looks like maybe, I don't know, maybe it's kind of leveling off and going closer to the 0. So that is one solution. This is basically one possible y of x that goes through the point let's say it this way, y of x through the point 0, 1/2. But notice if I picked a different point to force this thing to go through, I could force it to go through the point 0, 2 instead. So if I made it go through this point up here, it's going to start off even steeper, and it's going to be going steep immediately. And you could kind of trace it back, and maybe it's going to go through this point over here and then do something like that. Or I could start it somewhere down here on the bottom, make it go through the point 0, -1. If it has to go through, pass through this point, I'd get a solution that looks something like maybe this-ish. So we've got a lot of different curves that are all different possible solutions. So how is this possible? Well, this goes to the topic of an initial value problem. This was the section 1.2 that we kind of skipped. There are many solutions. The field, the direction field, basically defines sort of a family of solutions. I'm going to put that word family in quotes. It's not a super technical term necessarily, but a family of solutions. There's more than one solution. each passes through a different point. If we pick a different point to force our solution through, we'll get a different curve. So by picking different points to force our solution through, we get a bunch of different solution curves. Okay. So the question is why? What is this coming from? Why do we have a bunch of solutions? I've got this one equation. Why does it lead to a bunch of different solutions? Okay, I want to talk about kind of two things in regard to this. The first is, how are we mathematically going to solve this? And again, we're going to talk about the actual techniques in subsequent videos, but I want to talk about it very generally now. When we try to solve an equation in general, so even if it's just an algebraic equation, you can think of an equation as kind of being a knot. There were all of these different steps that were used to tie the knot. You may have a big complicated mess of a knot. To solve the equation is the same as untying that knot. You can't just start randomly pulling at the knot and expect it to come undone. You have to approach it in a methodical way. And in a sense, you have to undo every step that was done to tie the knot. You have to undo each of those steps in the reverse order that they were done to tie the knot. So whatever the last thing was that you did to tie the knot, that has to be the first thing you deal with when you're untying the knot. So the same thing is true when we start adding in operations like derivatives. We have to undo derivatives. As part of solving for y here, I need to undo the derivative. Right? So if our equation has a square in it somewhere, we're squaring the variable that we're trying to solve for. At some point, I'm going to have to take a square root to undo that square. Right? If I'm adding a number to the variable we're searching for, at some point, I'm going to have to subtract that number to undo it in order to solve for that variable. If I'm multiplying it by a number, I'm going to have to eventually divide by that number to solve for the variable that we're going for. And if I'm taking the derivative of our variable, I'm going to have to undo that derivative at some point. And how do we undo the derivative? With integration. So this is the first important idea. So let me say why. Why are we getting multiple solutions? Reason one. When we solve a differential equation, we have to undo the derivative that shows up in the differential equation. How do we do this? With integration. But if you think back to Calc 1 and Calc 2, when we talked about different integration techniques, which are going to eventually come into play when we start talking about solution techniques for differential equations, one thing always happened. Whenever you integrate a function, one thing is a constant that always happens every time you integrate a function. And I actually kind of gave it away there. You always get a constant. Integration introduces, and again, we're talking about indefinite integration here. We're trying to solve for a function, not an actual specific number. So all the integration we're going to be doing is indefinite integrals. But integration introduces a constant of integration, is what we call it, the plus c that you always get when you integrate something. So that plus c turns out to actually be really, really important. There's a reason that your calculus instructor would get mad if you neglected it from your answer. We care about the plus c. But having a plus c, when I eventually solve for this, means that I don't have a unique solution. I have a plus c. I have a constant that's unknown. And by changing the value of that constant, I can get potentially different solutions, right? If c is 1 or c is 2 or c is -1, it will affect what the solution winds up looking like in all of this. And so this is one reason that we get different solutions, non-unique solutions, the plus c term from integration. So the second thing I want to talk about is, okay, so what happens then if we've got this plus c, and this plus c means that we don't have a unique solution? How do we deal with that? So to find a unique solution, the plus c term must be specified. Essentially, we need to pick the value of c, pick an appropriate value. What that tells me is if our differential equation is enough to basically get a family of solutions, as we called here, so our differential equation, oops, let's get this all on the page at once. Our differential equation is enough to get a family of solutions, but we can see that there's lots of possible different solution curves. Then if we want a unique solution, we need more information. This equation isn't enough to give us a unique solution. We need an additional piece of information. And that additional piece of information is going to be the thing that will make our solution unique by determining the value of this sort of plus c term, so to speak. So to determine a unique solution, we have another unknown. We didn't just solve for y, we also need to solve for c. So the ODE allows us to solve for y, but that y will have this c term in it somewhere, but we need additional info. To solve for the c. This additional info usually comes in the form of an initial condition. And this again ties back to section 1.2 that we skipped. It was all about what are called initial value problems. Initial value problems are one where we specify an initial condition. Essentially, we specify a point that our y of x is going to pass through. And usually because it's an initial condition, and oftentimes we're thinking about this x-axis as opposed to being x, a spatial variable, oftentimes we're thinking of it as t, a time variable. The initial time is often thought to be 0. So oftentimes this will take the form y of 0 equals some particular value. And since we've already used c, I'll call it, I don't know, k. Doesn't matter. But we'll specify some initial condition. We'll say that the value of y at time 0, or the value of y at the initial position x, is equal to some particular constant. And by specifying this additional piece of information, it's enough to solve for that remaining unknown, the plus c term that showed up when we did our integration to solve for y. So this is the idea. Without specifying an initial condition, you are going to have an infinite number of solutions. All of these curves, I could have drawn any curve that kind of follows the pattern of these the lines in our direction field, there's literally an infinite number of possible solutions because of that plus c. But as soon as we pick that plus c term, we have tied ourselves to one particular solution. And we can do that by specifying a single point that our solution must pass through. Oftentimes, that single point takes the form of an initial condition like this that tells us the value of y at x equals 0 is equal to some value k. So essentially, you can think of this as being the exact same thing as specifying a point like this. In fact, if I wanted to rewrite this one up here, I could rewrite this as y of 0 equals a half. That's exactly what it's saying. When the x value is 0, what is the y value? 1/2. Y of 0 is 1/2. Therefore, it passes through the point 0, 1/2. And hence we get this particular solution right here. So this is the idea. A direction field will give us the whole family of solutions, but if we want a unique solution, we need to pick a specific initial condition that will allow us to find a specific solution. We'll come back to this later in the semester. It turns out there are other things you can pick other than an initial condition. And I'll give you just a highlight of this. We'll come back and again talk about this later. But this was a first order differential equation. So we had a first derivative that showed up, and we had to undo the first derivative. How do we undo that derivative? By integrating. But what if I had a second order differential equation? How do you undo a second derivative? You can't just integrate once, you need to integrate twice. And by integrating twice, you won't just introduce one constant of integration, you will introduce two constants of integration. So if I have a second order differential equation where I have a d squared y dx squared, so a y double prime term, I'm going to have to integrate twice in the course of solving for it, and I'm going to have two unknown constants requiring two conditions. And so we'll talk about this later on in the semester. We'll come back to how we can deal with this. Sometimes they're initial conditions that occur at the same point in time. We'll talk about what that looks like. Sometimes they're what are known as boundary conditions. And this is something that we'll talk again later on in the semester about, but definitely something that becomes important once you move on to partial differential equations, where you're doing differential equations usually in higher dimensions, or with respect to both spatial variables x, y, and temporal variables, time variables like t. And you have to have lots of different conditions in those cases. So just keep that in mind. Initial condition isn't the only thing that's possible to be used to specify the value of c, but for now that's all that we're going to care about. So hopefully that's clear. Okay, so now that I've talked your ear off about this one, let's try another example. Let's take a look at, let's not do it in blue. Let's go back to black. Let's try another one. So dy dx equals, let's say, x over y. This equation, when we specify the slope now, doesn't just involve y, it involves x and y. So we're going to have a slightly more complicated situation here. So let me start again by drawing our axes and picking some of the points that we're going to be interested in trying to find the slope at. So just make my grid here. Should have just put some graph paper on here so I don't have to do this every time. You're welcome, if you're doing your pencil and paper homework, you're welcome to just do some of these problems on graph paper if you have access to it, or if you wind up hand drawing your dots like I'm doing here, that's fine as well. So let's just say that's enough. And again, I'm not making this totally clear, but let's just, hopefully this is clear. That's 0, 1, 2, and so on. The scale here is similar to 0, 1, 2, and so on. I'm drawing those tiny because I don't want them to get in the way of the lines that we're going to be drawing. And then I'll put my table over here. So I want the x value, the y value, and then the dy dx, which is the slope. Right, so we're doing a geometric interpretation. And this is maybe, while I'm writing this out, is a good thing or a good time to point this out. There are really three interpretations of dy dx. The first is it's a derivative, and hopefully that's clear. So there's the calculus context. Dy dx is a derivative. But the physical meaning of that, as we described when we were dealing with all of our modeling problems, is we were always thinking of dy dx, or maybe it was dy dt, or dp dt, or temperature dt. It's a rate of change. And in the physics context, that's usually how we think of it. But when we start looking at our solutions, and in this case, solution curves, we're really thinking of it in a geometric sense. We're looking at pictures. And so we have the third interpretation after a derivative is equal to a rate of change, and that's that it is also equal to a slope. So derivative equals rate of change equals slope of a curve. And in this case, we are focusing on that geometric representation of it as a slope. But this solution up here that we drew, it's totally plausible that if this differential equation represents a population growth problem or something like that, this curve may represent the growth of population as a function of time. So we would have to tie together the graphical solution, a geometric picture of how things are going, to the actual applications, the physics solution or physical solution, what its interpretation is. So just keep that in mind. We really need to be good at kind of going back and forth between the different perspectives of just doing mindless calculus on the paper, remembering how to integrate and differentiate appropriately, and then also keeping in mind the applications and interpretations of the derivative, that it is both a rate of change and also a slope. Okay, so with that in mind, let me put some points down here. Let's do 0, 0, 0, 1. Let's do 0, -1, 0, 2. Let's do, I don't know, 0.1, -1, 1, 1, 1, 2. So far I'm only doing positive x values, but that's fine. I'll just stick with that for now. 2, -1, 2, 1. We'll come back to a bunch of these. So we'll maybe fill in more. I just picked these more or less at random, but let's take a look. Here is my differential equation. So my slope right here is going to be y over x. And maybe I should go back up to this one and fill that in. We said that it was equal to the slope, dy dx, but in this case it was just equal to y. This is how we actually calculate these values. In this case, it's equal to y over x. This is where I'm actually going to be getting the values I'm going to put here. The slope is x over y. You write that correctly. X over y, not y over x. So keep in mind that one thing this tells me is I can't let the y value be 0. This differential equation has something weird going on when y is equal to 0. So basically all these points along the x-axis where y is equal to 0, the slope is undefined. It's probably essentially infinite, right? When you take a finite number and you divide it by something approaching 0, something getting really, really small, that's essentially where vertical asymptotes occur, where the slope is going to infinity. So essentially what you can think of is there's probably vertical lines going through all of these points, but technically, strictly speaking, the slope is undefined exactly at each of those points. So this first one here, 0, 0, this is undefined. And this is going to happen whenever y is equal to 0, because we can't divide by 0. So let's do some of these other ones. This point, x is 0, y is 1. So what is x over y? Well, that's 0 over 1. That means that slope is 0. What about this one? It's going to be 0 over -1. That's still 0. What about this one? 0 over 2. Still 0. What about this one? So all I'm doing is taking x and dividing by y. X divided by y. So I'm taking the number on the left, dividing by the number on the right, and just writing down the result here. What is 1 divided by -1? Well, that's -1. What is 1 divided by 1? That is +1. What is 1 divided by 2? That's a half. What is 2 divided by -1? That's going to be -2. What is 2 divided by +1? +2. So let's go start filling in some of these. I'm going to, again, do it in another color here. So we already said it's undefined at all these points, but let's go to the point 0, 1. So that's this point right here. The slope is 0, which means it's straight horizontal right there. Same thing happens at the point 0, negative 1. That's down here. This is also horizontal. And same thing all the way down here, up here, I guess I should say, 0, 2. That also has a slope of 0. So basically all the points where 0, or where x is equal to 0, are going to give me a ratio of 0. So every single one of these points on this axis where the x coordinate is equal to 0, so all along the vertical axis, all those slopes are going to be 0. We only have this one point at the center that's undefined again. So we've already taken care of that one. So again, let me check all of those off. Let's go to the point 1, negative 1. So that's this one right here. It has a slope of negative 1. That means it's going to go in that direction. If I instead go up to this point, the point 1, 1, that has a slope of positive 1. And so I've checked off these two. If I go to the point 1, 2, it has a slope of a half. So that's going to be a little bit flatter. It's still uphill, but not quite as steep as this one right here. If we go to the point 2, negative 1, so 2, negative 1, that's here. That's going to have a slope of negative 2, so that's going to be steep downward. Over here, the point 2, 1, that is a slope of positive 2, so steep upward. And I've taken care of all the ones that we put in the table, so let's just think about them as we go. What is this point going to be? This is the point 2, 2. What is 2 divided by 2? That's going to be a slope of 1. Down here, the point 2, negative 2. What is 2 divided by negative 2? That is also going to be negative 1. And so that's going to be that same slope. This is the point 1, negative 2. So if I go 1 over negative 2, that's negative a half. So that's going to have a slope like this. It's still going down, but not as steeply as this one here. If we come over to the left-hand side, let's do some of those points. So what about the point negative 1, 1? What's negative 1 divided by 1? That is negative 1. What about negative 2 over 2? That slope is going to also be negative 1. What about this point here? Negative 1, comma 2. So negative 1 divided by 2. That has a slope of negative 1/2. So it's still downhill, but it's not as steep downhill. And over here, the point negative 2, comma 1. Negative 2 divided by 1 is going to be negative 2. So this is going to be an even steeper downhill. And what you'll notice is you can kind of start to see some symmetry here. This one is the mirror image of this one. This is the mirror image of this one. This one's where the mirror is, so it's the mirror image of itself. Same thing happened here. We can speculate that that's probably going to continue. Let's just verify that that's going to be the case. Let's try this point. So the point negative 1, negative 1. What's negative 1 divided by negative 1? That is positive 1. And sure enough, it looks like we're getting a mirror image continuation amongst these things. And that makes some sense. The points down here basically are the same as the points over here with only a single sign flipped, right? The x-coordinate here is the opposite of the x-coordinate here, but they have the same y-coordinate. So all we're doing is changing the sign of the slope and hence getting something that is going to have some symmetry. So it'll look like this, this, this. And you can go through and verify those if you have any doubts. So we get a picture that looks like this. Individual solutions, depending on our choice of initial condition, probably look something like this. Maybe they go out and then kind of go up like this. If I picked a different point, if I picked a point right here, it's kind of hard to know exactly what this looks like, but it probably does something similar and goes off like this and off this way. So I'm going to delete that one just to make it less confusing. Let's just stick with the one that we've already drawn. So I'll just say this is the one that we get if we do y of 0 is equal to 1. Passes through that point. So there's an example of one particular solution. But again, there's an infinite number of solutions that are possible. Okay, so hopefully what's becoming obvious as we do these is that they are incredibly tedious. And so I don't want to do a million examples of these by hand because in the long run, it's not a particularly useful skill, being able to come up with a table like this and just plot points and draw little segments of line with a given slope. I'm going to, in a separate video, show you how to do these using technology. So they can be done in MATLAB, they can be done in Desmos, and there's a program written in Java that I can post as well. And so I will post a video demonstrating how you can do problems like this, and it'll basically draw the picture for you in each of those resources. The one in Java and the one in MATLAB are better than the one in Desmos because they allow you to actually click on the curve or click on the picture somewhere and it'll draw the solution curve through that point. But on the other hand, the one in Desmos, even though it doesn't have that feature, it's also much easier for most people. So if you don't already have access to MATLAB, if you've never programmed in Java and don't have Java runtime environment on your computer, those might require some extra steps. You're welcome to do. I'll give you directions for how you can download those and do them. MATLAB costs a lot of money, unless you happen to be a UNM student, in which case you can get it for free. But I'll also show you how you can do these in Desmos, and it is by far the easiest. So take a look at that in a separate video. But just keep in mind, drawing these by hand isn't going to be a super important skill. I just want you to understand the idea behind what's going into creating these direction fields so that when you use technology to create these, it makes sense. You understand what's going on behind the scenes. So what I want to do now is instead shift gears just a little bit and talk about some of the behavior that we've seen. And in particular, I want to talk about a difference that showed up, if I can get this all on the screen at once, between these two differential equations. And there's an important difference. So it leads us to the topic of something called, zoom in enough that we can see here, something called autonomous equations. And this is another thing that can be used to categorize another classification for differential equations that's going to be useful to us, but we kind of needed these tools that we've introduced in order to introduce this idea, so I couldn't do it in that first video. But let's take a look. Essentially, the idea of an autonomous equation is that if the differential equation, so if the ODE takes the form of the following, if we get dy dx equals some function of y and y alone. So notice for these direction fields, the requirement was that we needed dy dx, our first derivative, equal to some function of both x and y. But in this first example, it wound up only being a function of y. And in the second example, it wound up being a function of both x and y. And I'm going to just remove this y from right here because it makes it hard to read. Let me put that y right there. It's a function of both x and y. The top equation is an autonomous equation. The bottom equation is not, because it has dependence on x here. So if the ODE takes the form of dy dx equals some function only of y, then it's autonomous. Right? And the important thing here is there is no x dependence, or no dependence on whatever the independent variable happens to be. Then it is called autonomous. And there's a nice feature of autonomous equations. So just real quickly, looking at the two examples that we had, dy dx equals y, that's autonomous. It's autonomous because the right-hand side is only a function of y. In our second equation, we had dy dx equals x over y, and that was not autonomous because it has some x dependence on the right-hand side. But it could be more complicated than that first one. It doesn't have to be as simple as dy dx equals y. It could be dy dx equals maybe 1 plus y squared. That is also autonomous. So hopefully this is clear. As long as the right-hand side is some function, it can have constants, whatever, but it just can't have any dependence on the independent variable x. It has to be just a function of y, or just a function of whatever variable we're trying to ultimately solve for. Then it's said to be autonomous. It turns out that these equations, happen to be particularly easy to understand, and they still happen to show up a lot in physics. So they're easy to understand. And still often relevant in physics. So in physics, oftentimes our independent variable isn't x, but is instead t. We're talking about something changing over time. In this case, the idea is that your rate of change, your dy dx, or in the case of physics, maybe it's dy dt, if it's only a function of y, it depends only on the current state. It is not time dependent. So in a physics context, so in physics, often the x is replaced with t, which is time. And basically, these types of equations show up as laws that are unchanging in time. So things like population growth. Doesn't matter if it was 100 years ago or 100 years from now, the population growth of a set of rabbits, put 2 rabbits in a cage, are going to have the same type of population growth in either case. There's no time dependence on what that model looks like. So autonomous equations model situations where there's physical laws, population growth, whatever, the Newton's law of cooling, but basically things that do not change in time. And I'm not saying that the solution doesn't change in time. I'm saying the laws that govern the solution don't change in time. So where the laws dictating the rate of change themselves don't change in time. Okay, that's a horribly phrased sentence there. I'm sure there's a better way to phrase this that I'm having a brain freeze right now and not able to come up with a better way of saying this. But basically, you can think of all the problems that we looked at in our examples in the previous video, where we are trying to come up with some law that governs how the rate of change occurs. Rate of change of the population growth, rate of change of temperature of our plate of cookies, rate of change of chemical concentration. And in many cases, those rates of change, those laws that govern the rates of change, are independent of time. These are things like population growth, like the temperature, Newton's law of cooling problems. So, Newton's law of cooling, population growth. Right? There's no time dependence in those models that we looked at in terms of dictating what the rate of change looks like. The growth rate isn't dependent on time. Okay, hopefully that's clear enough. And if not, it'll make more sense once we come back to those problems and start working on them in more detail. So when we're dealing with problems like this, autonomous equations, let me come back up here. Ones like this one right here that we said was autonomous because it only has y dependence on the right-hand side. What you'll see is exactly what I mentioned when we were working on this problem. Because the rate of change only depends on y, has no x dependence, essentially what you get is a picture where we look at all the different y values here, and if you shift that to a different x value, you just get an exact copy. So we really only have to do one column of solutions and then just copy and paste it at x equals 0, x equals 1, x equals 2, x equals 3, x equals 4, x equals -1, x equals -2, and so on. This column, oops, let me undo that. This first column looks the same as the second column, looks the same as the third column. They're all just shifted over because there is no dependence on x. The only thing the slope of these lines depends on is the value of y. So that is going to be true in all autonomous equations. And that leads to some useful approaches for getting a sense of the behavior. So we can easily get a sense of the behavior for these problems using something called a phase portrait. So a phase portrait or a phase diagram, both of these terms are used. So phase portrait or phase diagram, they're interchangeable terms. Okay, so let's consider an equation and I'll talk about what a phase portrait looks like for a specific problem. So consider, let's do this as an example, I guess. Consider an autonomous equation of the form, let's say we've got the dy dx is equal to y times a minus by, where a and b are constants that are both positive. Let's say a is greater than 0 and b is greater than 0. So a and b are both just some constants, some parameters in the problem that have been picked. Okay, so we have an autonomous equation because the right-hand side only depends on y. There is no x dependence on the right-hand side. We can figure out what the solution to this equation, this differential equation, is going to look like. We can basically come up with the direction field without having to plot all those individual points in a much easier way. And it starts by, instead of taking a geometric approach, going back and thinking about kind of a more calculus-y approach, in a sense. Points where the solution is unchanging are called equilibrium points, or sometimes they're called critical points, or sometimes they're called stationary points, so I'll write all of those down. But where it's unchanging, meaning i.e. if the solution is unchanging, if y is unchanging, what is dy dx? If it's not changing, what is its rate of change? Its rate of change is 0. So we're looking for points where dy dx equals 0. And they're called equilibrium points. So equilibrium slash sometimes called critical points slash sometimes called stationary points. All of these terms get used, so equilibrium or critical or stationary points. And they're going to be really useful. Let's think about where these points are. So for us, all I need to do is set dy dx equal to 0. So if I set dy dx equal to 0, it means this right-hand side has to be equal to 0. So y times a minus by has to be equal to 0. Hopefully one obvious place where this is going to be equal to 0, because I have it written as a product, y times this other term in parentheses. But if y is 0, then this whole product is going to be 0. So one of the solutions is going to be y equals 0. We can expect two solutions out of this, because if you were to distribute the y through, what you'd get in here is a y squared. We'd get a quadratic. And how many zeros or roots do quadratics have? In general, they have 2. So we're expecting 2 in all likelihood here. So the first one is y equals 0. And then the second one would be where everything in the parentheses is 0. And that would mean a minus by would be the thing that's equal to 0. And if we solve for y in this, so what I'm going to do is add by to both sides. I'll get that a is equal to by, divide both sides by b, and I will get that y equals a over b. There is our second point. So here's one point, y equals 0, and here's our second point, y equals a over b. Those are the 2 points that are our equilibrium solutions, the values of y that will be unchanging. So if we plot these points, we can start to get a sense of what the solution is going to look like. So let me get a graph again. So I'm going to have my vertical axis. Here. In fact, I can cheat a little bit. I'm going to do this horizontal axis closer to the bottom. So there's my x-axis and my y-axis. One of those critical points we just said was y equals 0. So it's going to be, I'll draw it kind of big so we can see it. It's right here at the origin. It's the point where y is equal to 0. The second one is at a over b. I don't know exactly where that falls, but I do know that it has to fall somewhere on the positive y-axis. Why does it have to be on the positive y-axis? Because I specified previously that both a was positive and b was positive. So if I'm taking a positive number dividing by another positive number, the result's going to be a positive number. So I don't know exactly where it is, but let's just say right here, there's the point a over b. So here's the point a over b. Down here, there's the point 0. If our solution happened to go through one of these points, so again, imagine we're trying to come up with some sort of whatever direction field, whatever it happens to look like, yada, yada, yada. I'm going to erase all those in a minute. But instead of having to come up with the direction field and then trying to draw one particular path through that direction field, I want to forget about these lines and see if we can come up with the path without those lines. That is our goal. So let's get rid of all those lines, which I drew randomly and are probably incorrect. And let's think about what this is going to look like. If I pick the solution to go through the point y equals a over b, what's going to happen to it? So I'm picking y of x, our graph, our curve that we're trying to graph, to go through this point. Well, if it goes through this point, by definition, it is unchanging, right? The solution is unchanging at that point. Another way of saying it is the slope is 0 at that point. If I start at this point, I'm going to stay at a height of y equals a over b. So if I start at y equals a over b, I'm going to stay at y equals a over b. And I'm never going to leave that, because if my solution starts here and it's unchanging, there's no way for the y value to ever change. And if the y value never changes, there's no way that the slope will ever change. And if the slope doesn't change, then the y value can't change. And sort of a circular argument there, but you'll stay on this point indefinitely. The same thing happens if I happen to have my initial point go through, in this case, the origin, y equals 0. We saw that if y equals 0, the slope will also be 0, and I will stay indefinitely on this point. So here's two possible curves of solutions. Here's what the curve would look like if y of 0 equals a over b, and here's what the curve looks like if y of 0 equals 0. Those are my solution curves. They're just boring horizontal lines. But what's going to happen everywhere else? So we've got two curves. What about the rest of the curves? So got two stationary solutions. They're these horizontal lines. Or another term for it, again, is equilibrium solutions or critical solutions, whichever term you want to do it. Maybe equilibrium is good, because equilibrium, to me, stationary and equilibrium both imply, in my mind, something that's unchanging. If you've achieved equilibrium, you're not changing at that point. Same thing if you're stationary, you are not changing. Okay, so we've got our two equilibrium solutions. What about everything else? So what about everything else? Okay, I want to think really quickly just about the right-hand side. We know the slope of our curve that we're eventually going to be drawing, right? We're going to try to draw the curve y of x. We know something about the slope of that curve. The slope of the curve is given by, in this case, coming back up to what we have up here. Where is it? It is, get it all on the page at once. It's right here. Y times a minus by. Same thing we had here. It's given by y times a minus by. Let's think about this as being sort of an f of y. This is our f of y. Let's graph f of y versus y. So I want to come up with a different graph where I look at f of y, which is defining the slope, as a function of y. So this is going to be weird. Let's forget about the graph we were looking at a minute ago, and let's just zoom into here. Forget about that other one for a minute. I'm trying to graph a picture of the slope, where the height of the curve here, the y value, or my f value, so to speak, I guess I should say, so the f value of my curve that I'm going to draw here corresponds to the slope of the graph that I'm going to draw over here. So we're removed, and I'm forgetting about the context, and I'm just trying to graph this. I have some function. All I have is f of y equals y times a minus by. Can you graph this function? Well, yeah, I can graph this function. We just said it's a quadratic. We already figured out the two zeros. We know that one of the zeros is at y equals 0. The other one is at y equals a over b, right? So there's two zeros of this thing. And I know it's a quadratic, so I know it's going to be a parabola. And I just need to figure out, is it a parabola that opens upward or opens downward? And if we distribute through, I'll get ay minus by squared. And it's clear if I look at the leading term here, the highest power of y, the y squared term that makes this a parabola, its coefficient is going to be negative. And that tells me this is a downward opening parabola. I don't know what it looks like. I don't really care much more than this, but what I care about is that it's positive in this region between 0 and a over b, and the values are negative out here on these other sides, to the left of 0 or to the right of a over b. And what I'm saying, I'm not talking about the slope of this. I'm literally talking about the function values. Where is this curve positive? Where is this curve negative? We'll worry about slope when we get to the other picture. But for now, this is just an upside-down parabola. It's negative to the left over here, right? These y values, or f values, I should say, are all negative. Over here, from here to here, the f values are all positive. And from here onward, the f values are all negative. Again, this axis being our f axis, so to speak. So what I'm going to do is just translate these over to the other graph. What are the values of f, which is now going to indicate slope, over here? Well, we just said between 0 and a over b, it's positive. It's positive between those 2 points. So I have a region where it's positive here. It's negative for all the values of y that are larger than a over b. So again, values of y that are larger than a over b. I'm taking what in this graph was the horizontal axis, The y-axis is horizontal here, and I'm just translating that over here. Over here, the y-axis is vertical, but I just want to copy the same information. I'm literally copying this y-axis, which is horizontal, to this y-axis, which is vertical. So it's positive here, negative up here, negative down here, based on this graph that we've got over here. What that tells me is over here, so these are the values of f. Right? This is our f of y. What is our f of y? Our f of y, this piece over here, is the slope. So I figured out where the slope is positive or negative by just graphing the right-hand side of, where is it? The right-hand side of the original equation, right here. By graphing this by itself as a function of y, f of y, I know where the slope is going to be positive, or my f of y rather is going to be positive, and where it's going to be negative. And over here I'm translating it and remembering, oh, by the way, that f of y that we just graphed over here represents the slope in the picture of the actual solution that we're trying to find. So this over here, this is the phase portrait. Or the phase diagram, and we're translating it to the actual original axes that we care about. This is the picture of the actual solution. So there's two different graphs here. The phase portrait is basically graphing the slope in and of itself, figuring out what the function that defines the slope looks like. That's our phase portrait. Over here, the actual solution graph, we're going to translate our phase portrait onto the appropriate axis and draw pictures. I know everywhere in between here, the slope needs to be positive. That means it's going this way. It's going upwards. Everywhere up above this point, it's negative. It has to be going downwards. Same thing here. Down here, it has to be going downwards. So all of my solutions in between here and here have to have positive slopes. My curves need to have positive slopes. But as I approach this line, if I were to ever get to this line somehow, what is the slope on this line? It is 0. This is one of our equilibrium solutions. And the fact that it's this unwavering horizontal line means it's impossible for my solution to somehow get to this line and then cross through it. The second you're on this line, you're stuck on this line forever. It's an equilibrium solution. Once you get there, you're stuck. There's no way to pass it. So even though my solutions all need to have positive slopes in here, I can't ever pass that line. And so what does that mean? Well, my solutions must eventually level off. And same thing down here, I can never pass this one on the bottom. So I must have a lot of solutions that start off very small positive slopes, get steeper, and then eventually level off again, going back to approaching a slope of 0. So here's a bunch of possible solutions that we could get in here. If I started right here, it would go up and then it would level off. What happens if I have a solution that starts up here? Well, it has to go down, but again, it can never cross that line. So it's going to approach that line, but never cross it. We'll get solutions that come downward and approach that line, but never cross it. Down here, we're going to have solutions that go down. They have to be close to 0 when we start near that point, but eventually they just take off down to negative infinity. And we can kind of get a sense of what the solutions look like. Once you've seen a few of these, you know that equilibrium solutions kind of are going to separate regions of positive and negative behavior. And that's true over here, right? Whenever you have a 0 on a graph, the only possibilities are that you're either going from negative to positive, positive to negative, or it is possible, although rare, to have a situation where your slope, or sorry, your function is positive, goes down to 0, and then goes back to positive. Or similarly, but with the negatives. That's also going to be a possibility. So we'll see more examples of stuff like that down the line. But for now, this is the idea behind a phase portrait. And phase portraits work great, but they only work for autonomous equations. So hopefully this makes some sense. We'll do a couple more examples down the line. You'll have some practice of this on the homework. But it brings us to a really important idea. This whole thing leads to the idea of what's called stability of our solutions. Are our solutions stable or unstable? And stability is basically what it sounds like. If a solution is stable and you kind of knock it a little bit, it'll go right back to where it started, right? If you have a table that's stable and you knock into it, nothing's going to happen. You'll bump it, but it'll, maybe rock for a second and then it'll go back to sitting the way that it's supposed to. But if you have something that's unstable and you bump it, it's going to fall over. It's going to take on a completely new state. Its position is going to dramatically change. And this is true of our solutions as well. So come back to this picture. Notice that one of our solutions, one of our critical points, I should say, one of our equilibrium solutions, this one right here, has all the solutions approaching it. Every solution is going to this value. So if I were to bump it, and instead of being right at this point, I were to bump off just to the side of this point, what's that solution going to do? It's going to go right back to the equilibrium solution. On the other hand, I have a second critical point where every solution is kind of going away from that line. What were to happen here if I were to, instead of having my solution be right at the equilibrium point, if I were to just nudge it ever so slightly off and start it right there instead? Well, it may start off staying kind of close to horizontal, but eventually it's going to take off and go negative and go way far away from this equilibrium solution. So this is the idea of stability. If the critical points, so let's just say this. One critical point in our example above has solutions that approach it. The other has solutions that, in a sense, run away from it. That, let's be a little more mathematical, that diverge from it. Ooh. From it. If all the solutions, when you nudge them away from it, they come right back to it, they come back and approach it anyways, that makes it stable. If they diverge from it when you nudge them, that's an unstable. So this one is our stable point, and the ones where they diverge, that is going to be our unstable solution. In physics, a good way to think about this is if we go back to the temperature problem, bringing the cookies out of the oven, we know that an equilibrium solution would be if your cookies start off the same temperature as room temperature, what's going to happen to the temperature of the cookies? They're going to stay that temperature indefinitely, right? There's no reason for them to change. Whereas if I perturb the initial temperature, so instead of being room temperature, if my cookies are a little hot, they came out of the oven, what's going to happen to the solution? They're going to cool down and eventually go to the equilibrium room temperature. They will stabilize to that value. So that is a stable equilibrium point. An example of an unstable one is a little bit harder here, but one example might be in population growth. This solution that we've drawn here actually is going to look a lot like those logistic growth equations that we talked about. When we had our population growth models, we had the simple one, the Malthusian model, that was just exponential growth. And then we had a second model that wound up being quadratic, and it actually looked a lot like this with kind of the A's and B's scaled differently. But it looked very similar to this. And it turns out, if you think of this as population growth, zero population is stable, right? If you start with zero bacteria, you're going to remain with zero of that bacteria indefinitely, assuming you've got a closed system, so a hermetically sealed petri dish or something like that. But if you start with even just one bacteria, what you would expect to see is the solution diverge away from the zero bacteria and eventually approach our carrying capacity of that petri dish. So starting with a zero population, technically, zero population is a stable or is an equilibrium solution, but it is an unstable equilibrium solution because you perturb it a little bit, and your population will take off and diverge away from zero. In this case, these negative values don't make any sense. They would be non-physical solutions in the context of a population growth problem. You can't have negative population growth, or negative populations, I should say. So keep that in mind. There's an example of a stable and an unstable equilibrium solution. One other thing that's possible, and that's something called a semi-stable critical point. So we've got unstable, stable, and now we have semi-stable critical point, or critical solution, or equilibrium solution. All of these terms, again, kind of mean the same thing. These are going to occur in the case that I talked about a minute ago. If I draw it here, let's say this is the equilibrium point, and so this is the equilibrium solution right there. Maybe this is our y value. Who knows where the x-axis is? But maybe on one side the solutions diverge away from that, but on the other, from the other side, they approach it. So from one side they diverge, and the other side they approach. So it's stable from below, unstable from above, if that makes sense, right? Up here, these solutions go away. Down here, these solutions go to it. And that would mean that this equilibrium point right here would be semi-stable. But notice, in both cases, the slopes above this point are positive. The slopes below this point are positive. This is exactly an example of a situation where if this is our critical point, if this is our phase portrait or our phase diagram, we have a case where our function, our f of y, is positive, goes down to 0, and then goes back to being positive. So, right, it's 0 at that point, but it's positive on this side, and it's positive on this side. This is the type of situation where you get a semi-stable critical point, where it goes from positive down to 0 back to positive, or alternatively from negative to 0 back to negative without actually crossing through from negative to positive or positive to negative. So this is what a phase portrait might look like. Again, positive down here, positive up here, but the slope is 0 right in the middle. If we, again, that's y, that's f of y, and that's y, and this is x. Okay. Got those labeled appropriately. So again, translating this axis to this axis. That's all we basically did.